Good morning, everyone. I'm Shiheng from the University of Science and Technology of China. Today, I will present our work, Amali, an analytical model for accurately modeling LLM inference on modern GPUs, in collaboration with my colleagues from USTC and SIAT. Large language models like ChatGPT and Llama have changed how we use AI, but running them is GPU intensive. These models heavily rely on GEMM operations and element-wise kernels, and they run on GPUs with numerous kernel launches, tensor cores, and complex warp behavior. To understand and optimize their performance and to guide architectural improvements, we need tools that are not only accurate, but also fast and insightful. Simulators are accurate, but too slow to be practical. Deep learning-based models are fast, but they are black boxes, and we can't tell why performance changes. That's why analytical models came in. They are fast, they are interpretable, and they are architecture-aware. In this section, we review prior analytical model based on interval analysis, such as GPU match, MDM, and the most recent GCOM. These models adopt a single warp abstraction. They pick a representative warp, then perform interval analysis to identify when and why the warp starts due to compute or memory dependencies. As shown on the right, they simulate an instruction issue timeline. Intervals indicated store cycles. Errors show issued instructions. Some instructions depend on earlier results, so stores occurred between them. While interval-based models provide us a foundation, real GPU performance depends on more than just dependencies. GPU match adds a multiple warp model to better capture GPU behavior. MDM brings in memory side contention, estimating queuing delays from MSHRs, NOC, and DRAMs. GCOM goes further, modeling modern GPU microarchitecture in more detail. Stores from limited compute units per subcore, memory stores from fewer L1 data cache banks, ideal stores caused by intra and inter-core load imbalance. It does this by breaking execution into finer-grade CPS stack components, leading to higher accuracy. However, previous method has significant limitations when applied to LLM inference. The first major issue lies in tensor core modeling. As we discussed earlier, LLM inference heavily rely on GEMM kernels that utilize tensor cores. But previous work directly applied CUDA core modeling approaches to tensor cores. Specifically, they used the initiation interval methods. Looking at the upper diagram on the right, let's assume we have a warp with 8 threads and 4 FP units. Due to insufficient compute units, the warp must be split across 2 cycles to issue. This is modeled using the initiation interval approach, where the warp size is divided by the number of functional units, giving the minimum number of cycles required to issue 2 independent instructions. But here's the critical difference. Tensor core doesn't work like that. Tensor cores use a collaborative execution way, where threads work together cooperatively. This fundamental difference means that for tensor core instructions, the number of issue and execution cycles is completely independent of both the warp size and the number of compute units. This collaborative nature of tensor cores makes the traditional initiation interval modeling approach fundamentally flawed when applied to tensor core operations, leading to inaccurate performance predictions for LLM inference workloads. Another important insight is instruction modifiers influencing tensor core behavior. We conduct an experiment when we modify the SASS instructions modifiers in a tensor core dominated benchmarks. The original instructions were HMMA 16.8.16. This means multiplying a 16 times 8 matrix with an 8 times 16 matrix to produce a 16 times 16 result matrix. We then changed the modifier from 16.8.16 to 16.8.8, which reduces the computational by half. Now we are computing a 16 times 8 result instead of 16 times 16. Everything else stays the same. Look at the left graph. The execution time dropped by exactly half from the blue point to the red point. This reveals something crucial about tensor cores. They operate at a fixed throughput. When we halved the computational workload, the cycles also halved proportionally. Even the number of instructions not change. This behavior is fundamentally different from CUDA cores. The right side shows how different initiation interval values affect modeling results. The blue portion represents delays caused by computing resource contention. Notice that GCOM's initiation interval value is twice our modeling approach, and the final results are also roughly twice as large. This demonstrates that the throughput-based method we propose significantly improves accuracy compared to traditional initiation interval approaches. The key insight is that tensor core instructions execute with predictable throughput characteristics, making the number of issues and executing cycle dependent of both warp size and the number of compute units. Beyond tensor core modeling, there's another critical limitation in existing approaches: ignored catch-miss scenarios that significantly impact LLM inference performance model. When we compared the store classification used in previous work with the actual hardware store types reported by ISCA compute, we discovered two major gaps. Immediate constant catch-miss and the instruction catch-miss stores were completely overlooked. The impact of this oversight is substantial. Looking at the bottom graph, our analysis of Llama 3 inference on RTX 3090 reveals that these two store types count for a significant portion of execution delays. Previous work did model some constant memory accesses through LDC and STC instructions. However, the more common pattern in modern GPU code is implicit constant memory access, where constant variables are directly encoded into instructions themselves. For example, an instruction like showed in green includes the constant access directly in the instruction encoding. This means that when this implicit constant access meets the immediate constant catch, they create stores that existing models simply don't account for. Similarly, instruction catch misses create executing bubbles that previous work ignored entirely. The last limitation is the uniform warp behavior assumption. Existing models assume all warps execute uniformly. But LLM inference shows significant instruction divergence. The histograms demonstrate this. Some warps execute hundreds of instructions, while others execute tens of thousands. This creates ideal cycles that previous analytical model completely miss, limiting their accuracy for modeling LLM workloads. Let's summarize the limitation. Existing models assume previous GPU performance modeling approaches face three critical limitations when applied to LLM inference. First is inaccurate tensor core modeling. Existing models directly apply CUDA core approaches using initiation intervals to tensor cores. However, tensor cores use collaborative execution where threads work cooperatively, making execution cycles independent of warp size and number of compute units. Second is ignored catch-miss scenario. Previous work overlooks two major store types: immediate constant catch-miss and instruction catch-miss. Third is uniform warp behavior assumption. Current models assume all warps execute uniformly, but LLM inference exhibits significant instruction divergence. To overcome these limitations, we propose Amali. It has 7 key components. SASS tracer dynamically capture SASS instruction traces from actual GPU execution using NV bit. SASS parser decoded SASS instructions to figure out operation types and data dependencies. Cache simulator models cache behavior to estimate average memory access time. Interval analyzer breaks down warp execution into intervals based on data dependencies. Interval parser examines each interval to identify stores from compute or memory throughput bottlenecks. KIR computation use kernel launch latency to model immediate constant cache miss and instruction cache miss. In interval parser, we capture stores caused by contention in memory and computing. For stores caused by contention of tensor cores, we introduce throughput-based method. We use instruction modifiers to determine the actual computational workload. We calculate the initiation interval using FAMA count from instruction modifiers divided by tensor core throughput from macro benchmarks. And we set the latency of tensor core instructions as the same value with initiation interval, reflecting the collaborative execution nature of tensor cores. The next is the kernel launch latency. We need to model constant memory cache misses and instruction cache misses. These stores mainly happen when kernels start up. We run empty CUDA kernels with different gray size and block size, then profile them using n-side compute. The profiling results show that the execution cycles of these empty kernels are dominated by these two types of stores, constant memory miss and instruction cache miss. From our benchmark data, we found that the kernel launch latency follows this formula, KL equals S times gray size plus K. The relationship is linear with gray size, but the slope S changes nonlinear with block size, so we use a quadratic function for S. All the coefficients came from benchmark measurements. The next is instruction divergence modeling. We calculate the difference between the max-minimum instruction count issued by WOPs on a subcore and the instruction from the subcore that schedules the representative WOP, then divided by the issue rate. Amali builds on interval analysis, but introduced 3 key improvements for LLM inference. First is CUDA core modeling, using throughput-based calculations instead of traditional initiation interval. Second is kernel launch latency modeling that captures cache-related store during kernel startup. Third is instruction divergence modeling that accounts for ideal cycles caused by WOP instruction divergence. Come to evaluation. We evaluated Amali on NVIDIA A100 using 3 benchmark suits. For LLM workloads, we test Llama 3 8 billion and 15 billion inference with different prompt lengths and batch sizes. For general GPU kernels, we use Rodania and DeepBench benchmarks. We compare against GCOM using real GPU traces and hardware metrics to ensure fair evaluation. Amali significantly improved prediction accuracy, reducing error from 127.6% to 23.6% compared to GCOM in Llama 3 inference modeling. For general GPU kernels, Amali again shows consistently lower error rates across all workloads. Amali enables accurate design space exploration for future GPU architectures. We simulate H100 with double A100 tensor core throughput and accurately predict GEMM kernel cycle reduction. Our approach uses A100's SASS traces with different GPU configuration to isolate architectural improvements. The results show Amali captures cycle reduction from A100 to H100 with prediction errors ranging from just 1% to 22%. The bottom graph shows our predictions closely track measurement performance across different metric sizes. They demonstrate Amali is accurate enough for early-stage GPU design space and exploration. Amali is a GPU analytical model for understanding LLM inference on GPUs. It models important things like tensor core behavior, constant cache misses store, and instruction cache miss stores, and WOP instruction divergence. It's fast to run and still accuracy, so it's useful for both software tuning and hardware design. Thanks for your attention. I'm happy to take any questions.